3I Atlas shows signs of non-gravitational acceleration. This phrase is not just a striking headline, it is the exact point where science pauses. It observes and asks itself if we truly understand how the universe works. Because what this interstellar object is doing does not entirely fit with the classical laws of gravity. It should not move like that, not with that subtle but constant deviation from its predicted trajectory, not with that energy that seems to arise from something more than the force of the sun. An Atlas was not born in our solar system, it comes from unknown regions between the stars. It crossed the void for millions of years, and now, as it approaches the sun, it is leaving behind a disturbing question. What is pushing it? Telescopes have detected the release of material, the formation of a coma, and possible jets of gases. However, some measurements suggest an acceleration slightly greater than what gravity can explain by itself. It is not fiction, it is not popular speculation, it is an observed fact, but still under analysis. If this is confirmed, we would be facing the second interstellar object after Oumuamua to show this behavior. But unlike Oumuamua, 3I Atlas does release gas and dust, which could offer answers or generate more doubts. And that is why, today more than ever, astronomers all over the world are following it minute by minute. Can you imagine witnessing in real time how an object from another stellar system defies our predictions? That is happening right now with 3I Atlas. Before we delve into the details of this interstellar visitor, there is something you need to do right now to join this global scientific effort. First, please give this video a like to help share this discovery with more observers. Second, subscribe to the channel and activate the notification bell to receive the latest real-time updates on its tracking. And third, scroll down to the comments section immediately and write the word Cosmos to add your name to the worldwide registry of people following this historic event. Please do this now. It was detected in 2025 by the Atlas system in Hawaii. Upon analyzing its orbital parameters, astronomers confirmed something extraordinary. Its trajectory is not elliptical like that of common comets, but hyperbolic. That means it comes from outside the solar system, and after passing near the sun it will leave never to return. But that is not the most surprising thing. The truly intriguing part is that its movement does not follow solely what gravity dictates. Small differences between the calculated trajectory and the observed trajectory drew attention. Those differences could be due to jets of gas expelled from its surface, as happens with comets. However, some values suggest an acceleration greater than expected, which opens the possibility of a non-gravitational acceleration. We are not talking about fantastic theories or hasty conclusions. We are talking about real data measured with professional telescopes and analyzed by observatories in different countries. What we still do not know with certainty is what is causing it. 3 Atlas is much more than a simple interstellar visitor. It is a real piece of another stellar system that traveled for millions of years before reaching ours, carrying information about how worlds form far from the sun. It was detected for the first time by the Atlas system, Asteroid Terrestrial Impact Last Alert System in Hawaii, when it barely showed a faint luminosity crossing the night sky. What initially seemed like just another comet quickly became an object of historical interest when its orbital calculations revealed that its trajectory was not closed, but open, hyperbolic. That means it is not gravitationally bound to the sun and that it had never been here before. Upon confirming this data, the International Astronomical Union classified it as the third officially observed interstellar object after 1I Oumuamua in 2017 and 2I Borisov in 2019. From that moment, ground-based and space telescopes began to monitor it intensely. Its speed, direction, and brightness began to be recorded with precision. Because every possible variation could reveal clues about its origin and its physical nature. It was determined that its orbital inclination was high relative to the plane where most planets orbit, which reinforced its foreign origin. Its speed was also greater than the solar system's escape velocity, another indicator that it does not belong to this family of bodies. But what drew even more attention was that unlike Oumuamua, which never showed clear signs of a coma or tail, 3I Atlas did begin to emit gas and dust as it approached the sun. Around its nucleus appeared a faint envelope of particles called a coma, typical of comets. This suggests that it contains volatile materials like water ice, carbon dioxide, or carbon monoxide that sublimate upon heating. That detail is crucial because it allows the study of how a comet that formed in another stellar system behaves under conditions totally different from those of the solar system. Despite showing cometary activity, the analysis of its orbital data revealed unexpected behavior. Small deviations relative to the purely gravitational trajectory. In simple terms, the object was not moving exactly where Newton's equations and the sun's gravity said it should be. Those differences were minimal but constant. For a common solar system object like a comet, these deviations can be explained by the expulsion of gas in the form of jets that act like small natural thrusters. However, in the case of an interstellar object, the scientific interest increases, because any non-gravitational behavior could reveal poorly understood physical processes or unusual materials. The initial calculations showed that the anomalous acceleration of 3I Atlas was not as intense as that observed in Oumuamua, but it was sufficient to be detected by precise astrometry. The observations were reported to organizations like the Minor Planet Center and analyzed by researchers from different countries. Some astronomers suggested that this acceleration coincided with the activity of gases expelled from the coma. Others pointed out that although that explanation is possible, the data are still not definitive to state with certainty the exact origin of that acceleration. What makes 3I Atlas such an important object is that it acts as a natural messenger from interstellar space. It is not the product of a simulation or a probe sent by humans. It is authentic matter originating from another solar system brought directly to us. Every atom on its surface, every dust particle that surrounds it formed under a star different from the Sun. Observing its composition, its behavior under solar heat, its brightness, its tail, and its possible fragmentation allows for a comparison of what worlds are like in other regions of the galaxy. The speed of 3I Atlas is another factor that makes it extraordinary. It moves at more than 26 kilometers per second relative to the Sun, which is equivalent to crossing the distance from Earth to the Moon in less than 4 hours. That speed allows it to escape the solar system once it completes its perihelion without ever returning. That is why every observation must be taken now, before it is lost definitively in the darkness. Unlike meteorites or interstellar dust particles that arrive on Earth in millimeter sizes, 3I Atlas has an estimated nucleus of several kilometers in diameter. This means it is large enough to preserve its internal structure intact since its formation. By studying how it releases gas, how it rotates on its axis, and how it interacts with solar radiation, astronomers can deduce properties like its density, its porosity, its ice content, and even its resistance to fragmentation. Every night, observatories in countries like the United States, Spain, Japan, Mexico, and Chile report new exact coordinates of the object to refine its orbit. The precise data enter mathematical models that calculate its future trajectory. Those calculations also serve to detect if its acceleration changes over time. If it increases, it could indicate that new volatile materials are being exposed as it heats up. If it decreases, it could mean that the surface layer has been partially depleted or that the nucleus is losing internal pressure. Up to this point, 3I Atlas remains a natural laboratory in motion. It is not fiction nor speculation. It is a unique opportunity to understand what lies beyond the solar system without the need to send spacecraft to other stars. But it is also a reminder of how much we still do not know. How are these bodies formed? How many exist? How frequently do they travel between stellar systems? And what chemical secrets do they carry with them? Non-gravitational acceleration is one of the most delicate and intriguing concepts within the study of objects like comets and especially interstellar visitors like 3I Atlas. It refers to any change in the speed or trajectory of an object that cannot be explained solely by the gravity of the Sun, the planets, or the classical laws of orbital motion. In most observed cases within the solar system, this phenomenon is associated with the release of gases and particles from the surface of a comet, which acts as a kind of natural thruster. However, when this behavior appears in an interstellar object, its significance acquires much more weight because it points to physical processes that could be different from those we know or more intense than usual. In the case of 3I Atlas, the first signs of a possible non-gravitational acceleration appeared when astronomers compared its predicted trajectory with its real position in the sky. These calculations are based on very precise laws of celestial mechanics that allow for predicting with great accuracy where a body should be found at certain times. When an object does not exactly match those predictions and the error is not due to failures in the observations or the influence of another massive nearby body, the possibility is considered that an additional force is acting upon it. In this case, that small difference between the observed and the calculated was consistent over several nights, which led to the suspicion that the object was being pushed slightly. The most accepted explanation among scientists is that 3I Atlas, as it approaches the Sun, is heating up and releasing volatile materials from its surface or from internal cracks. When those gases sublimate, they escape into space and carry dust particles with them. This process generates a recoil force that, although weak compared to the Sun's gravity, can subtly modify the comet's speed. That is the essence of non-gravitational acceleration, a force produced by the object itself due to its activity, not imposed from the outside. The behavior of 3I Atlas is not completely unexpected. Comets in the solar system often experience this type of acceleration, and astronomers have mathematical models to correct for them when calculating their orbits. However, what makes it exceptional is that it is a body that had never been heated by the sun before. Its surface, possibly composed of ices that formed far from any star, is reacting for the first time to solar radiation. This means that the gases present in its interior may be different from those in local comets and their release might not follow known patterns. The scientific interest grew even more when some research teams suggested that the magnitude of the observed acceleration was slightly greater than expected for the level of visible activity in its coma. This does not mean that it is something inexplicable or that it comes from technology, but rather that traditional models might not be correctly considering the composition, the structure, or the mass distribution of the object. Not all comet surfaces react the same to heat. Some release gas jets from specific regions, while others do so in a more diffuse manner. At this point, 3I Atlas has become an opportunity to improve those models. Astronomers also analyze the direction of that acceleration. In many comets, most of the thrust is directed away from the sun because the jets activate on the face illuminated by solar radiation. If the acceleration has lateral components or in directions not perfectly aligned with the sun, it could indicate that the nucleus has a complex rotation or that the gas is exiting from areas other than the illuminated ones. This allows for the study of the orientation of the comet's rotation axis, its spin period, and the distribution of materials on its surface. Another relevant scientific question is whether the non-gravitational acceleration remains constant, increases, or decreases. If it increases as the object approaches the sun, that confirms that new ice deposits are being exposed as the heat penetrates deeper into the nucleus. If it decreases suddenly, it could indicate that the surface crust has hardened or that the comet has lost internal pressure. In the case of 3I Atlas, the initial data shows smooth variations, which suggests relatively stable behavior, although with possible changes as it advances towards the perihelion predicted for the end of October 2025. It is important to note that the non-gravitational acceleration measured so far is small in absolute terms. It does not imply that the object is performing sharp maneuvers or that there are dramatic changes in its route. However, at an astronomical level, even a minimal variation can have great scientific implications because it reveals internal physical processes that cannot be observed directly. Every small change in the trajectory is like a footprint of what is happening inside the comet's nucleus. This type of analysis is not based on assumptions, but on real data obtained by telescopes in different countries. Observatories like Pan-STARRS, the Very Large Telescope in Chile, telescopes in Mexico, like the one at the National Astronomical Observatory in San Pedro Martir, and astrometry networks around the world are recording its position every night. These data are sent to the Minor Planet Center, where the orbital parameters are updated and it is calculated if additional terms are needed to explain its movement, including non-gravitational acceleration. In summary, what makes 3I Atlas special is not just that it comes from another star, but that its behavior is giving direct information about how an interstellar object reacts upon entering a planetary system. Every small change in its trajectory, every molecule that escapes from its surface allows for building a clearer picture of its origin, its composition, and its history. And while this happens, science observes with caution, without exaggerating, but also without ignoring what could become one of the most relevant discoveries of this decade. When 3I Atlas was first detected, its brightness was so faint that it barely stood out among thousands of objects monitored every night by the automatic search systems. The Atlas telescope recorded a moving light source that did not match the position of any catalogued asteroid or comet. In its first hours, it was provisionally classified as a possible comet due to its slightly diffuse appearance. But there was still not enough information to determine its true nature. Several nights of observation were required to calculate its initial orbit, and in that process, something powerfully caught the attention of astronomers. The orbital parameters were extremely eccentric and its speed was much greater than expected for objects belonging to the solar system. This led to immediately initiating more precise calculations to verify if it was an interstellar visitor. Within a few days, observatories in different countries began to report astrometric data. Each recorded position of the object allowed for refining its orbit. It was then confirmed that the eccentricity of its trajectory was greater than 1, a value characteristic of hyperbolic orbits. This means the object is not permanently trapped by the sun's gravity and that it arrived from interstellar space. From that moment, It received the temporary designation C 2025N1 before being officially recognized as 3I Atlas, where the 3I indicates it is the third recorded interstellar object and Atlas acknowledges the system that discovered it. As the weeks passed, interest increased. It was calculated that it would reach its closest approach to the Sun, perihelion, at the end of October 2025, at an approximate distance of 1.4 astronomical units. Although that distance is much greater than that of comets that intensely approach the Sun, it is sufficient to heat its surface and activate sublimation processes. Observations began to show a tenuous coma around the nucleus, a sign that the object does contain volatile materials. This immediately differentiated it from Oumuamua, which never showed clear signs of cometary activity. The coma of 3I Atlas grew little by little as it approached the Sun. Slight variations in its brightness were observed that could be related to its rotation, to the uneven exposure of its surface to the Sun, or to small gas emissions. Some telescopes managed to capture images where a faint tail directed away from the Sun was apparent, which indicated that solar radiation was pushing the expelled dust particles. This confirmed that the object was behaving, at least visually, like a conventional comet, but one originating from another star. Meanwhile, astronomers began to study its nucleus. It cannot be seen directly even with the most powerful telescopes, but its size can be inferred by analyzing the overall brightness and the amount of reflected light. Initial calculations suggest its nucleus measures between 2 and 5 kilometers in diameter. Although this estimate has uncertainty, it is sufficient to ensure that it is a significantly large body, capable of preserving its internal structure since its original formation. As data accumulated, small discrepancies were noticed between its expected position and its actual position. These discrepancies were not random, but followed a consistent pattern. To analyze them, scientists compared the data with gravitational models that include the force of the Sun, the planets, and solar radiation pressure. However, even considering all those factors, the orbit still showed a slight deviation. This was one of the first indications of a possible non-gravitational acceleration. The astrometric calculations showed that the additional acceleration had both radial and transverse components. The radial component means that part of the thrust seemed to be directed away from the Sun, which is consistent with the release of gases on the illuminated face of the object. The transverse component, although smaller, indicated that it might also be rotating, causing the gas jets to push in directions that change over time. This information suggests that the nucleus is not perfectly spherical and that its activity is not uniform. With each new observation, the orbital models are updated. The precision of these calculations is crucial, not only to understand the object's behavior, but also to predict its future trajectory, although it will never represent a risk to Earth. Knowing its path exactly allows for comparison with other similar objects and for studying how interstellar bodies interact with the Sun. During the months following its discovery, 3I Atlas was observed from large telescopes like the Very Large Telescope in Chile, the Subaru Telescope in Hawaii, and smaller but strategically located observatories that provide daily data. These observatories record its brightness at different wavelengths, which allows for studying the composition of the coma. So far, evidence of water, carbon dioxide, and possibly carbon monoxide has been detected, although more precise spectroscopic analyses are still being performed to confirm it. These compounds are common in solar system comets, which suggests that the basic chemical processes may be similar in other stellar systems. As it approached the Sun, it was discussed whether the object might fragment. Some comets, especially those exposed to solar heat for the first time, present internal cracks and break into several pieces. This happened with Comet C 2019 Atlas, which disintegrated before its perihelion. So far, 3I Atlas has not shown clear signs of fragmentation, although scientists remain alert, as a sudden rupture could totally change the way its evolution is interpreted. At this point in the observational history, 3I Atlas has gone from being a faint point of light to becoming one of the most monitored objects in the sky. Each new datum reinforces its scientific importance and at the same time opens new questions about its origin, its structure, and its destiny after leaving the solar system. Since its discovery, the behavior of 3I Atlas has been constantly monitored by ground-based and space telescopes, but it was from mid-2025 when its activity began to become more evident. As the object approached the Sun, its brightness progressively increased, indicating that gases and particles were beginning to escape from its surface. This release of material is a clear sign that it contains volatile compounds, something common in comets originating in cold regions, but especially relevant in this case because it is a body formed outside the solar system. The appearance of a coma, although tenuous at first, confirmed that solar heat was triggering sublimation on its surface or in shallow layers of the nucleus. The coma is not simply a structureless cloud of dust, it is a complex mixture of gas, sublimated ice, and microscopic particles that reflect sunlight. In 3I Atlas, it was first detected as a diffuse halo around the nucleus with a slightly greater brightness towards the region closest to the Sun. As the weeks passed, the shape of this coma became more defined and higher resolution observations allowed for the detection of a tail oriented in the direction opposite the Sun. This tail is the result of the pressure of solar radiation and the solar wind pushing the particles that detach from the object. Although it was not as long or bright as that of very active comets within the solar system, its presence confirmed that the phenomenon was real and measurable. One of the most interesting aspects was the detection of what appeared to be a gas jet emerging from a point on the nucleus. Telescopes like Subaru, equipped with high-sensitivity cameras, recorded a subtle linear structure extending from the central region of the comet in a direction slightly inclined relative to the main tail. This type of structure suggests that the nucleus does not release gas uniformly, but from specific zones where the ice is more exposed or where fractures exist. These jets are important because they can generate small but constant forces that slightly alter the object's trajectory, thus contributing to the non-gravitational acceleration that has been reported. To confirm if this behavior was real and not a visual effect, several independent observatories replicated the observations. The data coincided in the presence of a linear structure and in slight brightness fluctuations that could be related to the rotation of the nucleus. If the object rotates, the jets do not always point in the same direction, but change their orientation slightly, which would explain variations in brightness and in the direction of the observed acceleration. However, determining the exact rotation period remains a challenge, as the brightness variations are very subtle and can be confused with changes in the amount of material emitted. Another indicator of activity was the measurement of the gas production rate. Although it cannot be measured directly from the surface, spectra obtained with specialized telescopes allow for the identification of molecules present in the coma. In the case of 3I Atlas, signals compatible with water vapor, carbon dioxide, and possibly carbon monoxide have been detected. These compounds are commonly found in solar system comets, but the interesting part is that their proportion could indicate differences in the environment where it formed. For example, if carbon monoxide were present in a greater proportion than in solar comets, it would imply that it formed in an extremely cold place, far from its original star or even in an external region similar to the Oort cloud of another system. As the object advances, astronomers analyze whether the activity increases steadily or if it presents irregular peaks. In some comets, the activity intensifies suddenly when ice trapped under the surface finds a crack through which to escape. So far, in 3I Atlas, no abrupt increase has been recorded, but rather a gradual and sustained evolution, which suggests that solar heating is slowly penetrating new layers of the nucleus. This stable pattern facilitates the modeling of its behavior, although it does not rule out the possibility of more intense future changes, especially when it reaches perihelion. The morphology of the coma and how it interacts with the solar wind is also being studied. Depending on the speed and direction of the solar wind, the tail can curve slightly or present undulations. These deformations help determine the total amount of material expelled and the density of the interplanetary medium around the object. Furthermore, data from the Solar and Heliospheric Observatory (SOHO) and from the Parker Solar Probe are used to compare solar wind activity with the appearance of the tail of 3I Atlas on specific dates. A fundamental part of this analysis is precision astrometry. Every time the object is observed, its exact position in the sky is calculated with respect to reference stars. If that position is compared with where it should be according to gravity, one can calculate how much additional acceleration it is receiving and in what direction. The most recent data suggest that this acceleration is small but persistent, which coincides with the idea that it comes from the continuous release of gas. This phenomenon does not imply that the object is out of control or altering its course in an extreme manner, but it adds valuable information about its physical behavior. All this makes 3I Atlas one of the most studied objects today. Its activity offers a direct window into the processes occurring inside bodies that had never been heated by a star like the Sun before. Every jet of gas, every dust particle, and every minimal deviation in its trajectory is being recorded, analyzed, and compared with models. It is an opportunity to understand not only the object itself, but also the mechanisms that could be common in other stellar systems. The possible non-gravitational acceleration observed in 3I Atlas has generated crucial questions among astronomers, not because it represents something inexplicable, but because it opens the possibility of studying how an interstellar body reacts upon encountering the Sun for the first time in its history. The most accepted causes within the scientific community point to natural physical processes, mainly the sublimation of ices and the expulsion of gases from the nucleus. To understand this clearly, it is necessary to observe what happens when a comet formed in extremely cold conditions is exposed to a heat source as intense as the Sun. The ice molecules trapped inside the nucleus absorb energy, change from solid to gas state, and escape through cracks or pores on the surface. This gas, upon exiting, gently pushes the comet in the opposite direction, generating a minimal but detectable acceleration. The interesting part about the case of 3I Atlas is that it is an interstellar object, which means its chemical composition does not come from the solar system or from the Oort cloud. It formed around another star or in regions where the chemical and thermal conditions could have been different from those of the origin of local comets. This implies that the proportion of present ices like water, carbon dioxide, methane, molecular nitrogen, or carbon monoxide can vary considerably. If, for example, it contains greater quantities of carbon monoxide, this gas can sublimate at lower temperatures than water, activating much earlier when the object is still far from the Sun. That early activity could explain why the acceleration is detectable when it is not yet at distances where solar system comets normally show intense activity. Another possible cause being studied is the structure of the nucleus. If the nucleus of 3I Atlas is porous or fractured, heat can penetrate more deeply, sublimating internal layers of ice. As the gas accumulates in cavities, it can generate internal pressure and finally escape in the form of jets. These jets do not always point directly away from the Sun. Depending on the position of the crack and the rotation of the object, the gas can exit in different directions, generating radial and transverse components of the acceleration. This coincides with observations that show a slight lateral deviation, in addition to the expected deviation from solar pressure. It is not ruled out that the surface of the object is covered by a layer of dust that retards sublimation. This layer, called a dust mantle, forms when the more volatile ices sublimate and leave solid residues. If that layer is thin, the gas can escape without problem, but if it is thick, the gas becomes trapped and the pressure increases, provoking stronger, though less frequent, releases. This can explain eventual variations in acceleration, although so far in 3I Atlas no abrupt events of that type have been recorded. Thermodynamic studies are also fundamental. The balance between the solar energy the comet absorbs, the energy it reflects, and the energy it uses to sublimate materials defines how much mass it loses and how much recoil force is generated. The rotation of the object directly influences this process because it determines which zones receive more heat for longer. If the rotation axis is tilted relative to the Sun, some parts of the nucleus will heat up more than others. If the rotation period is short, the surface heats and cools quickly, which can produce irregular activity. If it is long, certain regions can accumulate heat and release gas in a sustained manner, which produces a more constant acceleration. An essential question is whether this acceleration is maintained, increases, or decreases over time. If it increases as 3I Atlas approaches the Sun, it would mean that more ice is being exposed. If it decreases unexpectedly, it could indicate that the surface has hardened or that the more volatile materials have already been expelled. Constant monitoring is what allows for the identification of these changes. So far, the data suggest that the observed acceleration is small and stable, which is coherent with a moderate emission of gas. The type of dominant ice in the nucleus is also considered. In solar system comets, the most common ices are water, carbon dioxide, and carbon monoxide. Water ice activates near 3 astronomical units from the Sun. Carbon dioxide activates earlier, around 5 astronomical units, and carbon monoxide can sublimate even farther away. If 3I Atlas shows signs of activity when it is still far from the Sun, it could be an indication of elevated concentrations of carbon monoxide or carbon dioxide. This can be confirmed through spectroscopic observations that analyze the object's light and allow for the detection of which molecules are present in its coma. Up to this point, there is no scientific evidence indicating artificial mechanisms, unknown forces, or phenomena not explained by physics. What is observed is coherent with natural processes, although in an environment distinct from the usual one, because the object originates from another star. That is why the behavior of 3I Atlas is considered not to contradict the laws of physics, but rather to confirm them in a different context. The study of these scientific causes does not aim to generate speculation, but to obtain information about how bodies form and evolve in other regions of the galaxy. Each datum about its acceleration, composition, brightness, or rotation helps to build a more complete model of how interstellar objects interact with the Sun. Furthermore, it allows for the comparison of its behavior with that of Oumuamua, which also showed non-gravitational acceleration, but without releasing visible gas. In that sense, 3I Atlas represents a unique opportunity to understand those phenomena with greater clarity, because it does present a coma and tail, which facilitates the study of the physical mechanism behind the acceleration. Although the phrase 3I Atlas shows signs of non-gravitational acceleration has begun to circulate in scientific and popular media, it is important to clarify that the astronomical community still treats this phenomenon as an indication, not as a definitive confirmation. The difference between both words is fundamental in science. An indication means that the data suggest something, but they need greater precision, repetition, and independent review before being considered a proven fact. That is why, although several research teams have detected slight deviations between the predicted and the observed orbit, there is still no official consensus issued by institutions like NASA, the European Space Agency (ESA), or the Minor Planet Center. The process to confirm a non-gravitational acceleration involves obtaining many high-precision astrometric observations over time. Each of those observations records the exact position of the object in the sky with respect to known stars. That data is compared with the trajectory calculated under the influence of only solar gravity, the planets, and radiation pressure. If the difference between both positions is consistent and always points in a determined direction, an additional term representing a small extra force can be incorporated into the models. That force is what is called non-gravitational acceleration. In the case of 3I Atlas, some preliminary calculations have suggested that this force is present, but the exact magnitude is still not defined with certainty, because the observations do not yet cover a sufficiently long period of the object's journey around the Sun. Institutions like the Jet Propulsion Laboratory, JPL of NASA, and the Minor Planet Center periodically update the orbital elements of the object. These updates include parameters like its perihelion, its eccentricity, its inclination, and its minimum distance to Earth. For now, the officially published data do not include a formal term of non-gravitational acceleration applied to the orbit of 3I Atlas. This does not mean it does not exist, but that it does not yet meet the level of certainty necessary to be incorporated into the system in a standard way. For that to occur, the data must show that this acceleration is constant, measurable, and not caused by instrumental errors, atmospheric conditions, or calibration problems between observatories. One of the greatest challenges for confirming this phenomenon is the required precision. 3I Atlas is located at great distances, and although its brightness has increased, it remains a small object compared to planets or satellites. Small telescope errors, atmospheric turbulence, or differences in measurement systems can generate deviations in its position that mimic a non-gravitational acceleration. That is why repeated observations from different places around the world and even from space where there is no atmospheric distortion are needed. Only when all that data coincides and shows the same tendency can the phenomenon be confirmed. Avi Loeb, a researcher from the Harvard-Smithsonian Center for Astrophysics, published an analysis suggesting that a non-gravitational acceleration could exist in 3I Atlas based on publicly available data. However, even he points out that the Minor Planet Center has not yet published official acceleration values for this object. He also mentions that more observations are required, especially near perihelion, to know if the acceleration increases, decreases, or behaves irregularly. His analysis is not a final confirmation, but an initial interpretation that seeks to open the debate within the scientific community. Other teams, like those from ESA and European observatories, have been more cautious and point out that although the behavior of 3I Atlas shows signs compatible with cometary activity, there is still no solid proof of significant non-gravitational acceleration. Some even mention that unlike Oumuamua, whose acceleration was detected a few months after its discovery, in 3I Atlas the evidence is not as clear because the cometary activity could explain a large part of the deviation without the need to invoke additional mechanisms. One of the most important documents for this type of analysis is the Minor Planet Center Circular. In these reports, official changes in the orbits of comets and asteroids are announced, as well as new discoveries. Up to this moment, the circulars related to 3I Atlas do not include formal terms of non-gravitational acceleration. This reinforces the idea that we are facing a phenomenon under study, not a definitive conclusion. Despite this institutional caution, the scientific community recognizes that the possibility is real and that it must continue to be analyzed. That is why an international observation campaign has been organized, involving professional telescopes, amateur astronomy networks, and shared databases. This global collaboration allows for tracking its trajectory almost in real time and comparing the results of different research groups. Another important aspect is that if the non-gravitational acceleration is confirmed, it would not mean that something unnatural or inexplicable is occurring. The most probable, according to current models, is that it is related to the expulsion of gas and dust from the nucleus. What it would provide is very valuable information about the amount of gas released, the rate of activity, the object's rotation, and the structure of its surface. It would also allow for the comparison of its behavior with that of Oumuamua, which showed acceleration without signs of a coma, and with 2I Borisov, which behaved like a typical comet, without showing anomalous acceleration. In conclusion, the official data show that 3I Atlas is an active interstellar object that is releasing material as it approaches the Sun. There are indications that this activity could be generating an acceleration that is not explained solely by gravity. However, the definitive confirmation requires more observations, greater precision, and exhaustive analysis. What can be stated with certainty today is that we are witnessing a real, measurable, and scientifically valuable phenomenon, whose study is still in development. Since humans began studying the sky with precise instruments, all observed comets and asteroids shared a common trait: they belonged to the solar system. That changed in 2017 when the first confirmed interstellar object was detected. 2 years later, 2I Borisov reinforced the idea that we are not isolated, but are occasionally traversed by fragments from other stellar systems. Now, with the arrival of 3I Atlas, science has for the first time 3 distinct examples to compare their physical, chemical, and dynamic characteristics. This comparison does not seek to generate sensationalism, but to extract real conclusions about how these bodies form and evolve far from the Sun. Oumuamua was the first and also the strangest. It did not present a coma or tail. Its brightness varied in an extreme manner and it showed a non-gravitational acceleration without detectable emission of gas or dust. That perplexed astronomers because without visible cometary activity it was difficult to explain why its orbit deviated slightly from what was expected. Some scientists proposed that the cause could be the degassing of hydrogen or nitrogen ice. Others suggested radiation pressure acting on an extremely thin body as if it were a sheet. The important thing is that although many ideas were proposed, the exact cause could never be confirmed with certainty. In contrast, 2I Borisov behaved like a traditional comet from the beginning. It had a well-defined coma, a clear tail composed of dust and gas, and its behavior could be completely explained through the sublimation of ices. Its spectra showed water, cyanide, and oxygen, in addition to dust particles similar to those of solar system comets. It did not show significant non-gravitational acceleration or anomalies in its trajectory. This gave scientists the first clear example of an active interstellar comet, similar to those we know, but with slight chemical differences. With 3I Atlas, something intermediate is occurring. Like 2I Borisov, it shows real activity, coma, dust, and possible gas emission. But like Oumuamua, it shows indications of a possible non-gravitational acceleration. The great difference is that in this case there is visual evidence of gas being expelled, which allows for the natural explanation of that acceleration without resorting to extraordinary mechanisms. This makes 3I Atlas the most valuable object for understanding how interstellar comets interact with the Sun, because it combines characteristics of the 2 previous ones: visible activity and a slightly anomalous trajectory. Another important comparison is its composition. Oumuamua never allowed for the direct measurement of compounds on its surface because it had no visible coma. 2I Borisov did allow it, and the results showed an abundance of carbon monoxide and water, which is consistent with solar system comets. In the case of 3I Atlas, the initial spectra suggest the presence of water, carbon dioxide, and possibly carbon monoxide. However, the analyses are still in progress and determining the exact proportion of these compounds could help identify if it originates from a cold region similar to the Oort cloud or from more internal zones of another stellar system. Size is also a point of comparison. Oumuamua was only between 100 and 200 meters, a small body probably fragmented before arriving here. 2I Borisov seemed to have a nucleus of 1 to 2 kilometers. In the case of 3I Atlas, the models indicate that its nucleus measures between 2 and 5 kilometers, which makes it the largest of the 3. This means it has sufficient mass to preserve its internal structure despite sublimation, making it more stable against the Sun's heat than other smaller comets. The eccentricity of their orbits is also similar in a key aspect. All are hyperbolic, which demonstrates that they are not bound to the Sun. However, the inclination and spatial orientation differ. Oumuamua entered from the constellation of Lyra, while 2I Borisov arrived from Cassiopeia. 3I Atlas has a considerable inclination relative to the plane of the planets, which indicates it is not related to any local comet stream. Each trajectory provides clues about the dynamics of objects expelled from other systems, possibly by gravitational interactions with giant planets in formation. A crucial point is how each one reacts upon approaching the Sun. Oumuamua did not show visible changes, but it did show slight acceleration. 2I Borisov showed constant activity without strange orbital alterations. 3I Atlas is showing activity and a possible acceleration simultaneously, which allows for the study of how sublimation affects its orbit in real time. This is valuable because for the first time an active interstellar object can be analyzed while also evaluating how that activity interacts with its trajectory. Another important aspect is its scientific significance. Oumuamua forced a rethinking of models about what type of objects can exist in other systems. 2I Borisov confirmed that interstellar comets similar to ours do exist. 3I Atlas contributes something more: the opportunity to measure with modern instruments the effect of solar heat on a large, active interstellar object with a coma, with a tail, and with a trajectory in constant adjustment. For science, it is not about seeking extraordinary explanations, but about taking advantage of a natural laboratory that traverses the solar system only once. The study of 3I Atlas is not limited to describing its trajectory or confirming if it really shows non-gravitational acceleration. Its importance lies in what this behavior allows us to learn about how interstellar objects interact with gravitational fields, solar radiation, and sublimation processes. Understanding these interactions offers clues to understanding how bodies form in other stellar systems, how they are expelled into interstellar space, and what happens when they enter a planetary system like ours. Each measurement, each image, and each spectroscopic datum contributes to building a more complete model of the phenomenon. One of the main scientific impacts is the possibility of directly comparing how an interstellar comet behaves relative to solar system comets. For decades we have known that local comets experience non-gravitational forces due to sublimation. But those models are based on nuclei formed around the Sun. By observing 3I Atlas, we are measuring for the first time how a body formed under another star reacts when it approaches our star. This allows for the evaluation of whether sublimation processes are universal or if they depend on the environment in which the object was born. If the data from 3I Atlas coincides with what we already know, the idea that comets are common products of stellar evolution will be strengthened. If they do not coincide, it will be a sign that important differences exist in the chemistry of planetary systems. Another relevant impact is the opportunity to study the internal structure of the object. The way 3I Atlas releases gas not only changes its brightness or generates a coma, it can also modify its rotation, its speed, and in some cases provoke surface fractures. By studying the direction of the non-gravitational acceleration and the changes in its rotation period, details of the comet's interior can be inferred, such as its density, its structural rigidity, and its porosity. These data are impossible to obtain in another way because no space mission has been sent to study it directly. The physics of its movement becomes a tool to decipher its composition. This object also reinforces the importance of improving the precision of astrometry, a branch of astronomy that measures the positions and movements of celestial bodies. To determine if a non-gravitational acceleration exists, extremely exact observations are needed. If several observatories in different parts of the planet record similar positions and those positions do not agree with gravitational models, it can be concluded that an additional force is acting upon the object. This process demands international coordination, well-calibrated telescopes, and advanced software to analyze data. That infrastructure continues to improve thanks to objects like 3I Atlas. The study of 3I Atlas also has an impact on the dynamics of the solar system. Each interstellar object offers information about how other planetary systems expel part of their material. Current models indicate that young giant planets can gravitationally alter icy bodies, throwing them into interstellar space. These fragments travel for millions of years and occasionally traverse systems like ours. If the non-gravitational acceleration in 3I Atlas is confirmed, evidence will be obtained that these bodies not only travel through space, but they can serve active structures capable of responding to new thermal and radiation conditions. Furthermore, knowing the trajectory of an interstellar object with precision has another scientific utility. It allows for the prediction of when it will be observed again in the future, if it will pass near planets, or if it will be lost definitively in deep space. In the case of 3I Atlas, it is known that its passage is unique. Once it crosses perihelion and moves away from the Sun, it will never return. That is why the next months represent the only opportunity in history to observe it. This temporal pressure has driven the scientific community to record all possible information before it disappears. The non-gravitational acceleration also has consequences for the understanding of the object's future trajectory. Although the deviation produced by the expulsion of gas is small, it can accumulate over time and affect its final trajectory when it leaves the solar system. This has implications for calculating its hyperbolic orbit with precision and projecting its journey in interstellar space. In broader contexts, it helps to design models that predict how many objects like this could pass near the solar system in the future and what their possible distribution of velocities would be. The study of 3I Atlas has also demonstrated the importance of combining observations from Earth with observations from space. Ground-based telescopes allow for the capture of deep images and detailed spectra, while instruments in orbit like Gaia or the Hubble Space Telescope offer more stable data, free from atmospheric turbulence. If at any moment the acceleration is detected to change rapidly, these observatories will be able to confirm if it is due to an increase in cometary activity or to changes in its orientation. Finally, another important scientific impact is the comparison between the three known interstellar objects. Oumuamua showed acceleration without a visible coma. 2I Borisov showed a coma without acceleration. 3I Atlas shows a coma and possible signs of acceleration. This sequence allows for the construction of a behavioral evolutionary line. In the first case, the acceleration was a mystery because there was no visible gas. In the second, there was no mystery because the behavior coincided with known physics. In the third, how the acceleration is directly related to the expulsion of material can be studied, which strengthens the link between observational data and physical models. 3I Atlas is not just an object traveling through the sky, it is a scientific tool capable of answering questions about the origins of planetary systems, the composition of icy bodies, the dynamics between gravity and sublimation, and the interaction between interstellar matter and solar radiation. Its passage through the solar system does not represent a danger to Earth, but a unique opportunity to measure how nature acts without human intervention and without speculations, solely through real data. Whenever a space object shows behavior out of the ordinary, as has happened with 3I Atlas, it is common for interpretations outside the scientific realm to arise. On social media, forums, and some communication outlets, the idea began to be posed that this object could be showing artificial signals or controlled maneuvers. However, science works under a fundamental principle. Any extraordinary claim must be backed by verifiable, repeatable, and consistent evidence. In the case of 3I Atlas, what has been observed up to now can be completely explained through known physical processes, without the need to resort to unproven hypotheses. Alternative theories arose mainly due to two elements: its interstellar origin and the possible signs of non-gravitational acceleration. The fact that it comes from outside the solar system naturally generates curiosity because it makes it an unknown visitor. The non-gravitational acceleration, for its part, aroused comparisons with Oumuamua, which showed similar behavior, but without emitting visible gas. In that case, some interpreted that it could be an artificial object or a probe. However, subsequent studies demonstrated that plausible explanations exist, such as the loss of hydrogen or nitrogen ice that could have generated that movement without the need for visible activity. In 3I Atlas the situation is different. This object does show cometary activity. A coma, dust, and possibly gas jets have been detected that naturally explain the small deviation in its trajectory. This means that the observed acceleration is coherent with the physics of comets. When ice sublimates due to the effect of solar radiation, the gas escapes and gently pushes the nucleus in the opposite direction. This mechanism has already been measured in solar system comets like 67P Churyumov-Gerasimenko, Halley, or Encke. The only different thing in 3I Atlas is that it originates from another star, but the physical processes are the same. Some videos and publications ask why, if the acceleration is natural, it has not yet been officially confirmed by NASA or the Minor Planet Center. The reason is scientific and has no relation to the concealment of information. For a phenomenon to be officially confirmed, it must meet certain criteria. It must be measurable with precision, consistent over time, and observed by multiple independent teams. In the case of 3I Atlas, the data are still being collected and compared. Detecting it a single time is not enough. It is necessary to observe how it evolves as it approaches the Sun and if the acceleration increases, decreases, or disappears. Until then, it is considered a hypothesis supported by indications, not a final conclusion. Another popular theory is that 3I Atlas could be a controlled ship or probe. From a scientific point of view, there is no evidence that supports that interpretation. No artificial radio signals, electromagnetic emissions with intelligent patterns, or metallic or geometric structures have been detected. The object's brightness corresponds to the scattering of sunlight by dust and ice, not reflections from constructed surfaces. Furthermore, its behavior coincides with that of a comet. It releases gas when heated, develops a coma and tail, and its acceleration can be explained by sublimation. Therefore, the artificial hypothesis has no basis in the data. It has also been suggested that the acceleration could be due to unknown forces or new physical laws. However, what is observed does not contradict Newton's laws or the principles of orbital dynamics. The small variations in the orbit of 3I Atlas fit within what is expected in an active comet. The Sun's gravity remains the dominant force, but the outflow of gas generates an additional impulse. This combination of forces has already been studied in solar system comets and forms part of the models astronomers use to calculate precise orbits. Science does not reject the unknown, but it does demand solid proof before accepting it. If at any moment a pattern that cannot be explained through sublimation, rotation, or radiation pressure were detected, then the door would be open to new hypotheses. But until now, no observation of 3I Atlas requires abandoning the known laws of physics. What is needed is to continue observing it to have more precise data and thus reduce the uncertainty. Speculations have also increased due to sensationalist headlines that seek to generate impact. Some media use phrases like, impossible movement, should not be happening, or scientists are baffled. The reality is different. Scientists are not surprised because they do not understand what is occurring, but because this is a unique opportunity to study an active interstellar object with modern instruments. The interest does not come from mystery or fear, but from the possibility of learning more about how comets behave outside the solar system. Scientific dissemination plays an important role in this context. Explaining clearly that non-gravitational acceleration is a natural phenomenon helps to combat misinformation. It is also important to remember that questioning, investigating, and debating are part of the scientific method. What is not part of the scientific method is affirming conclusions without verifiable evidence. That is why the work of astronomers focuses on measuring, analyzing, and publishing results in journals reviewed by other scientists. In summary, 3I Atlas does not need extraordinary theories to be interesting. Its value is in what it really is: a fragment from another stellar system that for the first time is being observed with a coma, with activity, and perhaps with non-gravitational acceleration. Understanding it does not mean imagining the impossible, but observing with precision what nature is showing. What makes this object special is not what it could be in the imagination, but what it is truly revealing through real data: how matter from other stars behaves when it enters the domain of the Sun. 3I Atlas is slowly approaching one of the most important moments in its trajectory, the perihelion, the point closest to the Sun. It is expected to reach that position at the end of October 2025, at an approximate distance of 1.4 astronomical units. Although this is far from the Sun compared to comets that pass extremely close, it is sufficient to heat its surface, activate more intense sublimation processes, and possibly increase the release of gas and dust. This event will be decisive for confirming if the non-gravitational acceleration mentioned in some studies is constant, if it intensifies, or if it disappears as the object heats up more. In this stage, telescopes in the northern and southern hemispheres are coordinating observations, because depending on its position in the sky, there will be periods where it is only visible from certain places on Earth. The network of professional observatories, along with well-equipped amateur astronomers, participates by sending position measurements that allow for the refinement of its orbit. Each new datum is analyzed and compared with previous models to verify if the object follows the calculated trajectory or if there are slight deviations. If those deviations persist, official terms of non-gravitational acceleration can be included in the models recognized by the Minor Planet Center. This process does not seek to confirm extraordinary theories, but to understand with precision how a comet formed in another stellar system behaves. For scientists, 3I Atlas does not represent a mystery or a threat, but an opportunity. It is a natural laboratory that travels through the solar system, bringing with it material that has never before been exposed to the solar wind or the radiation of our star. Its study could answer fundamental questions about how planetary systems form, what kind of compounds exist beyond the Sun, and if the processes we know in our comets are repeated in other parts of the galaxy. One of the main objectives for the coming months is to measure with greater precision the amount of gas the comet is releasing. This can be done through spectroscopy, a technique that analyzes light and detects which molecules are present. If the existence of water ice, carbon dioxide, or carbon monoxide is confirmed, the total mass that the object is losing as it approaches the Sun could be calculated. That loss of mass, however small it may seem, exerts a recoil force that modifies its orbit. This is the scientific basis of non-gravitational acceleration, and proving it with exact numbers is one of the most important aspects of the study. Another key question is whether the object will fragment. Some comets, especially those heated for the first time or with fragile structures, can break apart when the pressure of the internal gas surpasses the resistance of the nucleus. This already occurred with comets like C 2019 and 4 Atlas, which disintegrated before reaching perihelion. So far, 3I Atlas has not shown signs of fracture, but as it approaches the Sun, the thermal pressure on its surface will increase and new cracks could open. If this occurs, telescopes will detect sudden changes in brightness, the appearance of multiple fragments, or an accelerated expansion of the coma. It is also expected that the comet's activity will allow for the study of its rotation period with greater precision. When a comet rotates, the gas jets activate and deactivate according to the position of each region of the nucleus exposed to sunlight. This generates small periodic variations in brightness. Measuring those variations helps to know how long the comet takes to spin on its axis. With 3I Atlas, there is still no definitive figure, but it is suspected that its period could be between several hours and 1 or 2 days. If the rotation accelerates or decelerates during perihelion, that could indicate that the activity is affecting its angular momentum, which would provide information about the distribution of the gas and the structure of the nucleus. When 3I Atlas passes perihelion, it will begin to move away from the Sun and its activity will diminish. The coma will become less visible and eventually disappear, leaving the object without signs of sublimation. Afterwards, its speed will allow it to escape the solar system without ever returning. Unlike comets that return periodically, this is a unique visitor. It will leave behind only its data, its images, and its measurements, which will be archived for future generations of scientists. The study of the object does not end when it moves away from the Sun. On the contrary, the data obtained will be analyzed for years. They will be compared with what was observed in Oumuamua and 2I Borisov. They will be used to adjust models of interstellar comet formation and could influence the design of future space missions. Several agencies have considered that if an interstellar object is detected with anticipation in the future, it would be possible to send a spacecraft to study it up close. What is learned from 3I Atlas will help decide which instruments would be necessary and what type of trajectory should be used. Up to this moment, it can be stated with certainty that 3I Atlas is an interstellar object that shows cometary activity and that there are indications of a possible non-gravitational acceleration. What cannot be stated yet is that this acceleration is confirmed or that it implies phenomena different from the known ones. Science advances with caution, supported by observable evidence, not by assumptions. Each new observation can bring us closer to a definitive conclusion. What this object teaches us is that the universe is not static nor enclosed in borders. Fragments from other systems travel between stars and on rare occasions cross our path. And when that happens, we do not need to invent extraordinary explanations. It is enough to observe, measure, and understand what nature is showing. 3I Atlas is not a signal of something impossible. It is proof that interstellar space is full of stories formed far from here and that some of them, by chance, pass before our eyes.